Welcome to the last video in Unit 5, which is about double angle formulas. The reason they're called double angle is because if you take a look at every single one of these identities, the angle is truly multiplied by 2 or doubled. Now, eventually, it's going to be useful to know that sine of 2 theta is the same as 2 sine theta cosine theta, that cosine of 2 theta can be written as any of these three, and tangent of 2 theta is 2 tangent of theta over 1 minus tangent squared of theta. The question is, where do these come from? And so what we're going to do is use what the last videos were about, the sum formulas, to find that we're going to eventually get the double angle formulas from there. So if I start with sine of x plus x, the double angle formulas, if you think about it, 2 times an angle is the same as the angle plus the same angle. So if I use this idea here, that sine of x plus x would have to be sine of x, cosine of the second angle, which is also x, plus sine of the other angle, which in this case is x, and then cosine of x. If I have sine x cosine x plus another sine x cosine x, that means that there are 2 of them, 2 sine x, cosine x. So we have proven this identity, 2 sine theta cosine of theta, comes from this idea. If I want to find the tangent one, let's do tangent of an angle plus an angle. That is the same as tangent of the first angle plus tangent of the second angle, which is also x, over 1 minus tangent of the first angle times tangent of the second angle, which is all x. If I reduce that, tangent plus tangent is 2 of them, and tangent times tangent is tangent squared, which is the identity that I showed you earlier. Take a look. Last but not least is cosine. Cosine of x plus x would be cosine of x minus sine of the first angle times sine of the second angle. So that would reduce to cosine squared x minus sine squared x, which, if you look back at the identities, that is the first and the most popular of the 3. Now the question is, where did these other 2 come from? It has to do with substitution, and let me show you, at least for one of them. If I wanted to get this identity, if you took cosine squared x minus sine squared x, and you replaced the sine with 1 minus cosine from the Pythagorean identity. So you'd have cosine squared x minus 1 minus cosine squared x. That would get you, let's distribute in the negative, cosine squared x minus 1 plus cosine squared x. So that would be 2 cosine squared x's minus 1, which is where this comes from. If you wanted to find this identity from the original, you would replace cosine squared theta with 1 minus sine squared theta, and you would find this identity here. So I just wanted to show you where they come from. Now let's use these identities. One way that these double angle formulas are useful is when you're solving equations. You might remember from a previous video that whenever you saw an angle that had a 2 in it in front, that means it rotated twice. So we had to keep adding 2 pi. If you don't want to deal with that, you can change or use an identity to go from an angle that's multiplied by 2 to an angle that's not. We know that sine of 2x is the same as 2 sine x cosine x. So you would replace this with 2 sine x cosine of x, and then keep everything else the same, plus cosine of x equals 0. Notice now that all of your angles are just rotating one time, which saves us a little trouble later. So let's look at what we have with these 2 terms. I notice that you have a cosine in common. So I'm going to take a GCF out of cosine of x, and I'm left with 2 sine x plus 1 equals 0. Now this is the point that we need our unit circle again. So let me paste that in, and I'm going to keep it in terms of radians, because usually when we're solving equations we want radians for our answer. So what we would do here is we would set cosine of x equal to 0. We'd set 2 sine x plus 1 equal to 0. So this reminds you of the previous videos, I hope. Where on the unit circle, from 0 to 2 pi, so 1 rotation, is the x value 0? Here and here. So my answers would be pi over 2 and 3 pi over 2. And from this example, if you solve this and set it equal to 0, we would get sine of x equals negative 1/2. Where are the y values negative 1/2? Here and here. So this angle x value would either be 7 pi over 6 or 11 pi over 6 with one rotation between 0 and 2 pi. The next example, if I wanted to solve this equation from 0 to 2 pi, I notice again that I have a one rotation angle, but then I have a double angle formula or a two rotation angle. I don't want that there anymore. So the identity again for sine 2x would be 2 sine x cosine x, or 2 sine theta cosine theta. So I'm going to replace this with 2 sine of a cosine of a, keep the sine of a that was originally multiplying, and still set that equal to cosine of a. A lot of the times with equations, it's useful to have it equal to 0. So let me reduce this a little bit and move this over. There's a sine of a times another one, so I'm going to write that instead as 2 sine squared a cosine of a minus this cosine of a equals 0. Just like the last problem, I notice I have a greatest common factor of cosine of a. So if I take that out, I'm left with 2 sine squared of a minus 1 equals 0. Now this reminds me of an identity. Let me see if it exactly matches. If I go back to my double angles, I have 1 minus 2 sine squared theta. Here it's 2 sine squared theta a minus 1, which isn't exactly the same. So I'm not going to replace an identity. Instead, I'm just going to set both equal to 0. Cosine of a equals 0, and 2 sine squared a minus 1 equals 0. Again, let me just paste in my unit circle here. So if I take a look at my unit circle, just like last time, the cosine of a, or where x is 0, is at pi over 2 and 3 pi over 2. So that's done. The second part, if I solve this, let me add the 1 and divide by 2. So sine squared of a equals positive 1/2. Sine is not alone yet, so I'd have to take the square root of both sides. If I do that, I would get sine of a equals, the square root of 1 is 1, so I have plus or minus 1 over. Now 2 is not a perfect square, so we'd have to leave that as root 2. Now, because I can't have a square root in the denominator, if I multiply top and bottom by root 2, I would get root 2 over 2 as a possibility. So we look at our unit circle and say, where is my y value positive or negative root 2 over 2? Well, that would be at any 45-degree based angle. So this would have 4 answers because of the plus or minus. My answers would be at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And what's so nice is because I used my double angle formulas to replace the rotation, I don't need to rotate these angles at all. So double angle formulas are very useful for solving equations. They are also useful for simplifying expressions. We would like to find sine of 2, this is alpha, cosine of 2 alpha, and tangent of 2 alpha. I will change these all to x's just to be a little easier. Now, we are given just the cosine of x is negative 2/3, and we're given a quadrant. So just like the last video, I'm thinking about drawing a picture. It's between pi over 2, or 90, and 180, which means that my triangle is in the second quadrant. My angle, or reference angle, is x, and I'm given that cosine, or adjacent over hypotenuse, is there and there. I knew this had to be negative because it's in the second quadrant. If I do the Pythagorean theorem and figure out what this length is, we would have 9 minus 4, so this would have to be the square root of 5. And positive because y is going up. So if I want to find these values, I can use the identities I just figured out. Sine of 2x is the same as 2 sine of x cosine of x. So again, just like the last video, even though I don't know what x is, I do know what these ratios are because of my triangle. So sine of x is really opposite over hypotenuse, or root 5 over 3. Cosine of x is negative 2/3. So if you think of this 2 as 2 over 1, we can multiply straight across and get an answer of, let's see, negative 2 times 2 is negative 4 root 5 on the top, and then I have a 9 on the bottom. I can't reduce 4/9, so that crazy thing is my final answer for sine of 2x for the double angle formula. If I would like to find cosine of 2x, I have my choice of 3 different identities. My favorite is cosine squared minus sine squared, so I'm just going to use that. I know cosine squared x minus sine squared x for the double angle. I don't know what the squareds are, but I do know what cosine is. I know that the ratio for cosine is negative 2/3, and then I would just square it. Minus the sine ratio is root 5 over 3 squared. If I simplify that, negative 2 squared is a positive 4, 3 squared is 9, minus root 5 squared is 5, root 3 squared is 9. If I combine these, my answer is negative 1/9. Lastly, if I would like to find the tangent of 2x, that identity is 2 tangent of x over 1 minus tangent squared x. So let me write that down. 2 tangent of x over 1 minus tangent squared of x. If I look at my triangle, I know what the tangent ratio is. Tangent is going to be, sorry about that, tangent is going to be root 5 over negative 2. So if I come down here, this is the same as 2 times root 5 over negative 2 over 1 minus the tangent ratio root 5 over negative 2 squared. Let's simplify this. Good news up here, 2 on the top, 2 on the bottom, these cross out, and I'm just left with the negative root 5 on the top. In the denominator, I have 1 minus, let's see, root 5 squared is 5. This is a negative 2 squared, which is a positive 4. The way this looks kind of ugly, so I'm going to get a common denominator on the bottom. This 1, if I wrote it in terms of fourths, would really be 4/4 minus 5/4, which is negative 1/4. So this is negative root 5 over negative 1/4. If I multiply by the reciprocal, because I'm taking a fraction divided by a fraction, this is the same as negative root 5 times the reciprocal of negative 4 over 1. Negative times negative is a positive. Specifically, my answer is a positive 4 root 5. So just like the last video, the triangle is going to help you find the ratios that you need to find every single one of these, even if you don't know what the angle is up front. As one more tidbit before I leave you, you could have found tangent a different way. Remember that tangent is sine over cosine. So you could have said that tangent of 2x is really sine of 2x over cosine of 2x. And we already found these two ratios. We found that the answer to sine of 2x was negative 4 root 5 over 9, and we found that the cosine of 2x was negative 1/9. So that's the same as negative 4 root 5 over 9 multiplied by the reciprocal, negative 9 over 1. These would cross out, and so my answer would still be a positive 4 root 5. Either way is awesome. This way you might be thinking is faster. Go for it. If you see it, go for it instead of this identity. All right, guys, this is the end of Unit 5. You definitely will be practicing for an upcoming test. Thank you for sticking with me throughout this entire unit. Good luck with the final exam.